Have you ever looked up at the night sky, seen a tiny speck of light, and wondered just how far away is that star? Is it a close neighbor, or is it in a galaxy far, far away? It seems like an impossible question to answer. I mean, we can't exactly stretch out a giant cosmic tape measure, right? But what if I told you that for over 2,000 years, humanity has been cleverly measuring the heavens, and today, we can pinpoint distances to objects billions of light years away with incredible accuracy. It's one of the greatest detective stories in science, and it all starts with a simple trick you can do right now. Hold your thumb out at arm's length. Now, close your left eye and look at your thumb. Then, switch eyes close, your right eye, and open your left. See how your thumb appears to jump against the background? That's called parallax. The apparent shift in your thumb's position is due to the different viewpoints of your two eyes. The distance between your eyes is the baseline. The farther away your thumb is, the less it seems to jump. Astronomers use this exact same principle to measure the distance to nearby stars. But instead of using two eyes, they use two different positions of the Earth. They take a picture of a star, and then 6 months later, when the Earth is on the opposite side of the Sun, they take another picture. The distance between these 2 points is huge, about 300 million kilometers, or 186 million miles. This massive baseline makes even distant stars appear to shift slightly against the backdrop of much more distant stars. By measuring this tiny shift, this stellar parallax, we can use simple trigonometry to calculate the star's distance. It's the most direct and reliable method we have, and it's the first rung on what astronomers call the cosmic distance ladder. The parallax method is fantastic, but it has its limits. Once you get beyond a few thousand light years, the parallax shift becomes too small to measure accurately, even with our best telescopes. So, how do we measure things that are farther away? We need a new rung on the ladder. And for that, we need to find standard candles. Imagine you're in a completely dark field, and you see a single candle flame in the distance. How far away is it? It's hard to tell. It could be a faint candle that's close by, or a very bright candle that's far away. But what if you knew exactly how bright that candle was supposed to be? What if you knew it was a standard 100-watt light bulb? Then, by measuring how dim it appears from where you are, you could calculate its distance precisely. A dimmer bulb means a greater distance. This is the idea behind a standard candle in astronomy. It's an object whose true brightness, or luminosity, we know. One of the most important standard candles is a type of star called a Cepheid variable. These are special, pulsating stars that get brighter and dimmer in a very regular, predictable pattern. In the early 1900s, a brilliant astronomer named Henrietta Swan Leavitt made a groundbreaking discovery while studying thousands of these stars. She noticed a clear relationship. The brighter the Cepheid, the longer it took to complete one pulse cycle. Its period of pulsation was directly linked to its intrinsic brightness. This was a game. Now, astronomers could find a Cepheid variable star anywhere, even in a distant galaxy. They just needed to measure the time it takes to pulse. From that period, they know its true brightness. Then they measure how bright it appears to us. Comparing the two tells them the distance. It's like every Cepheid comes with its own built-in distance marker. This method allowed the legendary astronomer Edwin Hubble to make one of the most profound discoveries in history. He used Cepheids to measure the distance to the Andromeda Nebula, proving it wasn't a gas cloud in our own galaxy, but a separate, massive galaxy. Millions of light years away, the universe, in that moment, became vastly larger than we had ever imagined. Cepheid variables are great, but they're still just stars. To see them, we need to be able to resolve individual stars in a galaxy. For galaxies that are even farther away, we need an even brighter standard candle. We need something that can outshine an entire galaxy, even if only for a short time. We need a supernova. Specifically, a type Ia supernova. These are not just any stellar explosion. They are the result of a very specific, violent event. It happens in a binary star system where a small, dense star, called a white dwarf, is orbiting a companion star. The white dwarf's powerful gravity pulls material off its companion, sort of like a cosmic vampire. As it gains more and more mass, it approaches a critical limit about 1.4 times the mass of our sun. known as the Chandrasekhar limit. Once it hits that limit, it can no longer support itself. The result is a runaway thermonuclear explosion that is unbelievably bright. For a few weeks, a single type Ia supernova can be as bright as 5 billion suns. And here's the crucial part. Because they all explode at almost exactly the same mass, they all reach almost exactly the same peak brightness. They are fantastic standard candles. When we spot one of these explosions in a distant galaxy, we know its true luminosity. We measure how dim it appears, and Bhumi can calculate the distance to its host galaxy, even if it's billions of light years away. So we have parallax for nearby stars, Cepheids for nearby galaxies, and type Ia supernova for distant galaxies. Each rung on the ladder allows us to calibrate the next. We find nearby Cepheids, whose distance we can measure with parallax. This calibrates the Cepheid period luminosity relationship. Then, we find a galaxy that's close enough to see its Cepheids, but which is also hosted at type Ia supernova. This allows us to calibrate the true brightness of the supernova. It's a beautiful, interconnected system, building our knowledge step by step, farther and farther out into the cosmos. But there's one more method, the grandest of them all, that takes us to the very edge of the observable universe. It doesn't rely on individual objects, but on the universe itself. This is where Edwin Hubble comes back into the story. After measuring the distances to many galaxies using Cepheids, he noticed something strange. He measured the light from these galaxies and found it was stretched out, this redshift is a cosmic version of the Doppler effect. Just like the pitch of an ambulance siren drops as it moves away from you, the wavelength of light from a galaxy moving away from us gets stretched towards the red end of the spectrum. What Hubble discovered was that the farther away a galaxy was, the faster it was moving away from us. This relationship, now known as Hubble's law, was the first evidence that the universe is expanding. The fabric of space-time itself is stretching, carrying the galaxies along with it. This discovery gave us a whole new way to measure distance. Now, for the most distant objects, we can simply measure their redshift. The amount of redshift tells us how fast it's receding, and using Hubble's law, we can infer its distance. This method allows us to estimate the distance to quasars and galaxies so far, a way that their light has been traveling for over 13 billion years to reach us. We are literally looking back in time to the dawn of the universe. From a simple thumb trick to the expansion of the entire universe, the story of cosmic distances is a testament to human ingenuity. It's a ladder we built ourselves, rung by painstaking rung, through decades of observation, insight, and discovery. Each new method allowed us to see farther, to understand more, and to grasp our true place in the cosmos. So the next time you gaze at the stars, remember that those tiny points of light aren't just beautiful, they are puzzles that we, against all odds, have learned to solve. We've measured the universe, and in doing so, we've discovered just how magnificent it truly is. Thanks for watching. If you enjoyed this journey through space, don't forget to like this video and subscribe for more simple science explanations. See you next time.